Hello there, welcome to your 11th webinar. In this webinar, we are going to have a walkthrough to your third project, which is Voice User Interface. More specifically, you are going to build a model, which as an input, we are going to have an audio file of somebody's talking, and as an output, you're going to have its corresponding text. More specifically, this Jupyter notebook is divided into three parts. The first part is pre-processing, which it includes the lowercasing, removing the punctuation, removing the stop word, and so on, and also feature extraction. This step one has been already done for you. The only thing that you need to do is to just run these cells, and it will do all of the job for you. And as a second step, you have to build a model, and more specifically, we'll build 6 models, which the last one is going to be optional for you. So let's go through each of this model, just talking very shortly what should you do. For your first model, you have to build a very simple RNN model, which this RNN model can be either RNN in itself or LSTM or GRU. For your second model, you have to add a time distributed dense to your RNN layer. For your third model, you have to add a CNN and also time distributed dense to your current RNN model. And for your fourth model, you have to deepen your RNN layer, which it means adding more layer to it, plus the time distributed dense layer. And for your fifth model, you're going to have a bidirectional RNN and plus time distributed dense. For the last model that you have to build, by the way, this is optional again, you will look through all of this model that you have built so far, and you will see which of them perform the best, and you will take them and you will combine them, and you will put that in your last model, which this can be result in quite a high accuracy. And at your last step, you're going to have a prediction. So the dataset, let's go to talk about dataset. The dataset that you're going to use is called library speech, and this is contain thousands of hours of speeching and its corresponding text. We give it to neural network. But for your project in here, we are only going to use a subset of that dataset just because of the speed purposes and also for computation. So if you run this cell, you are going to have your labels, which is text, and also your inputs, which have already been pre-processed, and also the feature extraction applied to it. And there is two types of feature extraction, one is spectrogram and NFC. Both of them are available for you, and you can use either of it. And after that, running this cell, you will see your audio file and you have a chance to actually play it. So let's start by our first step, which was pre-processing and feature extraction. So as I said, the pre-processing step has been already done for you, and the only thing that you have to do here is to choose either you want to use spectrogram or MFCC, and you do not need to write any code for it. You only need to choose from either of these two, and you can use both of it, and at the end you will see which of them result in a higher accuracy. Then you will use that instead. But in most of the cases, MFCC will work better for you. So if you want to know more about like how to actually do this feature extraction, I have already covered that in our last webinar. And let's take a look at this. If you go here, for creating your spectrogram, you only need to do a couple of lines of code. At the very start, you will load your audio file using Liberosa. You will use a Fourier transform on that audio file, which is this line. After applying the Fourier transform, you will make your spectrogram, which it will result in this. It's just a few lines of code if you use the Liberosa library. And for your MFCCs, again, even is simpler. The way you will create your MFCC is to first load your audio file. After loading it, applying the MFCC again using the Liberosa library. And after that, scaling it using scalearn. And this will be the end result. And usually this type of feature extraction, if you look at it, in our x-axis we are always going to have time, and in our y-axis we are going to have frequency, which its unit is hertz. So all of this feature extraction, either spectrogram or MFCC, will create this type of thing, which we on x-axis we are going to have time, and also on y-axis we are going to frequency. That's the only thing that you need to remember for our feature extraction. So if you line these lines of code, it will exactly show you the feature extraction that you're going to use. So that being said, let's go to the next step, which is creating your own model. Before that, make sure you're actually using GPU, because it is a very high chance that at some point while you're training, you're gonna receive an error and it's going to be a whole lot of mess. And if you don't have any GPU, you can use Google Colab. It's totally free, and you can take advantage of their GPU. So let's start with our first model, which is going to be a simple RNN. So for this, let's come back to this Jupyter Notebook. And in this part, this is the exact step that you can take in order to finish this part successfully. And for sure, it is not the only way. There's a lot of other ways, and this is just one of the ways that it will work. So for your first step that you have to do is to create an input using keras_layer.input. And for your input shape, you want to specify none and input dimension. Input dimension, the reason we want to specify this because you can use either spectrogram or MFCCs, and depending on which one you're going to use, this input dimension is going to be different. This 161 is input dimension if you're using a spectrogram, and if you're using MFCC, it's going to be 13. That's why we want to specify that. So let's come back to this. For your second step, you want to create a GRU layer, which it will return the sequences, and also have an implement mode of 2. If you look at the documentation, you will exactly see how to specify this implementation mode of 2. After that, you want to use a softmax activation function. Then you want to finalize your model using keras_model.model. And after you finalize your model, you have to change your output length, which the way you're going to change it is to specifying the model.output length, and you have to change it in a way that is exactly the same amount of the output theme. After changing your output dimension, you can start training your model using train model. This is something that you have imported, and it will take care of all of the stuff. So if you look at it inside, you have to only put your model and that's it. So for your second model, you want to add a time distributed dense to your current RNN layer, and the steps that you have to take is going to be very similar to your first model. At the very start, you have to create an input dimension, input layer using keras.layer.input with again input dimension of none and input dimension, and this is going to be different depending on the feature extraction that you are using. Then you want to create a GRU layer, which it will return the sequences, and also it has a implement mode of 2. Then you can add a batch normalization layer, and this will for sure will increase your accuracy at some point. Then you will create your output, which is dense with the output dimension, and you will wrap a time distributed layer around it. After that, you will use a softmax activation function, and you will finalize your model using keras.models.model. Then at your 7th step, you have to change the output length, which you can just specify it with model.output length. Then you'll make it equal to be same as this output dimension. And at the end, you will use this train model that you have already imported to train your model. Okay, now let's talk about the third model that you have to build. If you look at the picture that has been already provided for you, in here we are going to have our input. Then you have to put them inside the 1D CNN layers, and after that you will put it into your RNN, and after that you will put it on a time distributed dense layer and then output layer. If you just look at this, you will see you can exactly implement this model. So the way you will do it, as a very first step, again, create your input using keras.layers.inputs, and you also have to specify the shape as none and input dimension, and this input dimension depends on the feature extraction that you are using. As a second step, you want to add the conv1D, which is one-dimensional convolution layers. For your third step, you add a batch normalization layer, and for the fourth step, you can use either of RNN layer like LSTM, GRU, RNN. The choice is yours. So I use a LSTM layer, which it returns the sequences, and also it has the implement mode of 2. Then you want to use a batch normalization layer, and if you look at this, after this RNN we have to implement the time distributed dense layer. So that's what we are going to do. We are going to have a dense layer with output dimension, and also a time distributed layer is wrapped around it. For your 7th step, use a softmax activation function, and for your 8th step, finalize your model using keras.models.model. And for the 9th step, you have to change the dimension of your output, because for now it is not the same thing as the output name. And what you want to do is to use model.output length and make it equal to this output name. And as your last step, you want to train your model using this train-model. So let's go to the fourth model that you have to build. If you look at the pictures, in here we are going to have our inputs, and then we are going to have our first RNN layer, the second RNN layer, and then we are going to have a time distributed dense, and at the end we are going to have our output. The steps that needs to be taken in order for finishing this model: again, creating your input using keras.layers.input, and also specifying the shape as non and input dim. For the second step, you will use a LSTM layer. Again, the choice is yours. You can use GRU2 LSTM layer, which it will return the sequences, and also it has the implement mode of 2. Then use a batch normalization layer. Batch normalization layer. And for your second RNN layer, you can copy paste exactly this, which is going to be LSTM layer, which it returns the sequences, and also it has an implement mode of 2. Again, add a batch normalization layer, and after that use a dense layer with the output dimension, and add a time distributed layer around it. For the next step, use the softmax activation function, and then finalize your model using keras.models.model. And like previous models, you have to change the dimension of your output, which you will do it with model.output length, and you have to change it in a way it will be comparable with this output dim. And for your last step, you want to train your model using train model that you have already imported. Okay, for your fifth model, if you look at this image, you're going to have your input, then you will add your bidirectional RNN, and then you will put the time distributed dense layer, and then output. So the steps that you need to take for finishing this part is to create an input using keras.layers.input, and then put a shape of non and input dim, which is going to be depend on the type of feature extraction you used, which it was, I think, 161 if it was spectrogram, and 13 if it was MFCC. Then you will create a GRU layer, which returns a sequence and also has an implement mode of 2. Then you will create a bidirectional layer, which is wrapped around this GRU layer. Then you put a dense layer with output dimension. Then you will add a time distributed layer, which is going to be wrapped around that dense layer. At the next step, you will use a softmax activation function, and then you will finalize your model using keras.models.model. Then again, you will change your output using model.output, so it will be compatible with this output dim. And for the last step, you want to train your model using train.model. For your final model, as I said, it is totally optional. You do not need to do this, but it's a very fun thing to actually continue it, because so far you did a lot. So in here, the only thing that you need to do is to see which of this model that you have created resulted in a high accuracy. Then you will combine those strategies and you will put it in your final model. So the steps that I took for this model is as follows. The first thing that you need to do is to create an input using keras.layers.input, and for its shape you want to define an input dim. And the reason, again for the last time, the reason we are using this is because depending on the feature extraction that you're using, this input dimension can be different. For your second step, use a bidirectional layer which is wrapped around the GRU layer. More specifically, this GRU layer is going to return the sequences, and also it's going to have an implementation mode of 2. After creating your bidirectional layer, add the batch normalization layer, and then use a ReLU activation function. For your fifth step, again use a bidirectional layer which is wrapped around the GRU layer, and more specifically this GRU layer will return the sequences, and also it has an implementation mode of 2. For your sixth step, add the batch normalization layer, and for your seventh step, use the ReLU activation function. And lastly, for your last layer, create the dense layer, which it has an output dimension as a shape, and use a time distributed layer which is going to be wrapped around this dense layer. Now at the very last, add just this softmax activation function, and then use keras.model to finalize your model. After finalizing your model, change the output using model.outputLength, and make sure that it has the shape is output.dim. And for your last step, train your model using this train model. Of course, for your final model, you can do a lot more, that it can higher the accuracy a lot. So this was just one strategy, that with just this strategy for sure you can reach to above 95% accuracy rate. And also one thing to notice is that in here, after creating your model for speech recognition, after that it predicts what is this audio file saying, there's a high chance that there's going to be some problem with its pronunciation. Like, it might say write some words wrongly. It doesn't mean the model did a bad job. The only thing is it will write it in a wrong alphabets. So if you want to take one step further, you can use some autocorrection, like it will correct that word that it's been written in the wrong alphabets. And if you're interested for further resources, either for creating your own model from scratch or using API, for sure check out these resources. There's also some API that with literally simple lines of code. Let's check this out. With just few lines of code, you can have your own speech recognition, which this API is from Google, so you're sure that it's gonna have a very high accuracy rate. So that's it with this webinar. I hope it was useful for you, and thank you for putting your time in it, and see you for the next webinar. Thank you.